most important operation in arithmetic, which is addition. Essentially, if I know how to do addition, I'm done. Everything can boil down to a number of additions. Then if I have jumps, a memory, and an adder, I can do all the calculations I want to do. It will be just a matter of time to eventually finish them before I die, but that's a different story. You know, again, there are some jokes of Papami. You may or may not like them. Okay, I like that. You can't add apples and oranges, son. Only the government can do that. But I won't comment on that. Okay, now, when we speak about addition, we rely on two fundamental building blocks, which are the half adder and the full adder. Remember, all our story, it's a bit of a high-level story, but relies on Boolean algebra and relies on implementation of basic building blocks with Boolean gates. You don't have to do that in CMOS, or you don't have to do that with Boolean algebra as long as you can deliver this behavior. Then my mathematical approach relies on full adders and half adders. You may implement them in a different way. However, if you have another kind of technology which will produce easier other sort of building blocks, you may want to change the paradigm, and all the story that I'm telling you today may end up in being useless. You know, maybe you learn how to count on a stone kind of adder, you know, with stones, which is called abacus. Okay? Then if I want to use an abacus and build an abacus with CMOS, that won't work. It won't be a natural construction. However, I can build an abacus with single electron tunneling jumps. Then I can see electrons as stones, and I can do calculations by moving electrons in my system. Don't laugh, because this has been proposed. Actually, I've been doing that. It's one of my research projects. I'm not trying to make any propaganda for it, because I'm not active in that direction any longer, but it's just for you to understand that a change in the foundation, in the technology, in basic building blocks may change the paradigm. Now, for now, we rely on those. I assume you guys, you know those, right? Nobody has a problem with that. This is the beautiful, oops, I was not supposed to be online. I should do something about that. These are the dot representations. Then I have two dots, which are 2 bits, and I represent them as 2 dots. Then my half adder is not doing much, or not. Actually, it is doing a lot. It's taking 2 dots which do have the same weight. They are in the same column. Doesn't matter which column is that. And it's producing 1 dot in the current column and 1 dot in the next column, which has a weight which is twice as large. Then 1, 1 will result in 1, 0, which is 2 in binary. The same story when I have 3 dots. This is the full adder. Result can be between 0 and 3. Then 0, 0, 1, 1. Then what half adders and full adders are doing what we call compression. We take numbers which are written with more dots, and due to the fact that I'm using the weighted system, I am writing them with less dots. The half adder is not really doing a compression, it's doing a rewriting, but this one is really doing a compression. Okay, now, how do I implement those guys? I can implement them in many ways. Those are 3 implementations of a half adder. Which one is your favorite? Or do you have a favorite one?
No.
Okay. I would like to ask the guy in Eindhoven who is enjoying what is now breakfast or lunch, but I know I cannot hear you. Then you can continue enjoying your food. Which, by the way, is not polite to do that during the class. Then I just have to rely on a local answer. The communication with remote places is half duplex. Then, do you prefer any of those?
No.
Yes?
Number B.
Number B. Why do you prefer B?
XOR is difficult to implement, and the bottom one uses one more gate than another gate, and it has an incorrect table.
Okay. Each of them do have advantages and disadvantages. And at the first glance, you are right.
NAND, I think, have better implementations on CMOS.
Then, NANDs are a natural born killer in CMOS because of the inverter. Then I like NANDs. The fact that this is coming in an inverting format may or may not be disadvantageous. At the first glance, you are right, but NORs are slightly slower than NANDs because they rely on more PMOS transistors, which are slower than NMOS transistors. Again, this is for microelectronics. The carriers do have different kind of, I should not say that kind of words because you get pissed off on me, right? Then we prefer NANDs because they are faster. Okay? PMOS transistors are slower than NMOS transistors. And there is something else, which, you see, this gate, an XOR gate, I can actually implement in one gate if I do some tricks and I play in the proper way with transistors. In a CMOS implementation, I have what is called the pull-up network and the pull-down network. And I can implement XOR like an AND or invert gate. I will not draw that implementation, but you might be curious to take a look on how this can be done. Then basically the answer as usual is, depending on your technology, you may choose one or the other. What is important and is good for me is to have a carry which is coming as soon as possible because the carry is going to the next position. The faster the carry is calculated, the better for the calculation in general. Then fast carry, it's one criterion. The others are like this. NMOS are natural constructions. You have an inverter and you want to make an AND, it's simple. I know you like me to draw transistors, right? This is the inverter, this is the P, this is the N. If I want to make an AND, I add here another guy, okay? And then this is the one which is doing the calculation. This is called the pull down because those transistors are, this is an on. These are the transistors which are, pulling down the network, and they are in series. Because they are faster than the P, it's better to put here transistors in series. If I have an OR, I have to put here in series, PMOS. Anyway, this is something that you are supposed to know, right? You don't look happy. Are you not happy because you don't know it? Should I ask at the exam things like that, to play with transistors? Why not? The right answer is because we don't care. We do computer arithmetic. We play at high level. Who cares about CMOS? You can implement full adder also in many ways. This is a hierarchical implementation which we rely most of the time on in order to construct circuits. I have basic building blocks and I apply hierarchical constructions. I can also rely on muxes. This is something which you will probably, or you didn't see in your studies, assuming that you studied some kind of logic design. Then, or you can go for that kind of standard representation, or you can also go for that kind of representation, which maybe you didn't hear about. This is called transmission gate. Then I will compute, not based on gates, on Boolean gates, I will compute based on transmission gates. Then a transmission gate, it's a pair of P and N in parallel, and whenever I'm driving those with a 1, this will conduct. Whenever it's a 0, this will not conduct. Now, I can make a max, a multiplier, with just 2 transmission gates in this way. Then I will select this or that, depending on the value of x. Now, if I make a max with normal gates, yes, do you know how I do that? I can write the equation. The output is z. Z is equal with x0 times y plus x1 times y prime, or the other way around. I don't know if I did it wrong or correct. Then this is my selection, and these are the 2 values. If I want to implement that, I apply De Morgan, right? F double bar is equal with F. I'm kind of speaking now Korean. I will not say Chinese because some of you can speak Chinese, which will end up in this kind of implementation. That I need an inverter, 1 NAND gate, 1 NAND gate, 1 NAND gate. Was my Korean okay? Now, this is more complex than this. Why are we not learning this in school, and why are we not using that all the time? The question is again for microelectronics, but embedded system students may answer. You are my customer.
It's non-regenerative.
It's not?
Non-regenerative.
Okay, then you know. Then what is happening is that when I have this kind of gate, I'm losing the signal. While the inverter kind of construction is regenerating the signal all the time. Then when I apply something at the inverter here, it might be a weak signal, but it will be regenerated by the inverter or by the gate. While the transmission gate, which will be here, will take some of my signal. Then I can put a transmission gate or a couple of them, assuming that the signal here will be strong enough to be properly regenerated by the inverter. Then this is a good implementation, it's fast, it's cheap. However, I have to be sure that here and there I put inverters or buffers or other CMOS gates in order to regenerate the signal. Okay. Are you a microelectronics student? Yeah. You see, finally, I see my dream. And you didn't know that. Shame on you.
You make me go for microelectronics course.
Why?
You make me feel bad.
No, but you know, there are people which are doing computer architecture, and they say, we don't care about what's happening under us. Under processor architecture, there are many things which do happen. And if we don't understand them, we do not make the right choices. Arithmetic is one thing, but logic design and fabrication technology do also contribute. I'm not an expert in those. Neither are supposed some of you to be. But you have to understand them because they influence your decision. Sometimes your decision is actually determined by phenomena which are one level under your abstraction level, or even 2 levels down. Now, I have full adders, I have registers, those are my basic building blocks, and I want to make an addition. The simple way to make addition is the serial addition. And I will take the operands in the same way you learn to do addition in primary school, from the least significant position, and I will do addition one position at a time. Then I take this, I do the addition, I produce this, and I transfer, which in my time was kind of saying that I will remember that for the next position. This is the carry. And then I move my focus to the next position. I have this, which I remember from the previous calculation. Now I have 3 dots, and I compress them to a sum and a transport. This is the principle of addition, which you call ripple carry addition. Because this carry, this transfer, you remember it, and you use it next time. Now, the cheapest way to do an addition is to do series. Then you have your operands into registers. You always start the addition from the least significant position, because you cannot start from the most significant position. It won't make sense. In some representations you can do that, that's called online arithmetic, and it's a different story. But in what we do here, you always start from the significant bit, because carries are propagating from this significant towards more significant position. Then I take a pair of bits, I give it to the full adder. The full adder is doing calculation, which is I'm producing a bit, and I'm storing the carry in this latch. Then one full adder, one latch are enough in order to do n bit addition, n being 1 billion, 1 trillion. It will just take 1 trillion of those cycles in order to complete it. I don't have to store it. If it is, it's okay. If it is coming on a channel or 2 channels, I can also have an output channel, and I don't have to store it. But generally we store the operands and we store the result. Now this is slow in the sense that it will take n cycles in order to complete an n-bit addition. Now, the second approach which I can think of is to unroll this. Instead of repeating the calculation with the same full adder, I copy now n full adders and I chain them. And I do the same kind of trick, right? I do addition here, I propagate the carry, do addition here, propagate the carry, and I claim this is better. Now, why do I claim it's better?
Because it's done in one clock cycle.
Sorry?
Because it's done in one clock cycle.
Will that be true? How long that clock cycle will be?
Well, it will be longer than the other one. But
Then I'm just measuring the time, right? It will take me 1 clock cycle, but how long that cycle will be? There is something in that direction, but you didn't reach yet the destination. There is something related to timing. And what I did is I made an investment. Then I replicated the full adder n times. Then the first reaction of somebody which is, very careful with money will say, no, that's not good because this is expensive. But I don't care about the price. What I care is the performance. Yes?
Pipelining?
What do you mean by pipelining?
Now that you can already start having new numbers after the last one is complete.
Which of them?
The bottom one.
On the bottom one. To do pipelining, I have to put registers, which I don't have to. And also, I have no clue whatsoever what pipelining is yet. The reason why this is better, I'm trying to solve this problem in parallel because these guys will operate in the same time. Then when they get the operands, they will start computing. Eventually, carries will come, and they will have to reevaluate. Then somehow the process is still serial. and I can see it as a long cycle which will take the delay of this full adder, and this full adder until I complete. Then if the delay of the full adder is 1 unit, this will take n units. You may say that this takes n units too, but there is an overhead. I'm storing the carry in a latch or in a flip-flop. Do you remember things like hold time? Then the latch has some overhead. In order to get the value inside, I have to keep that value stable for some time, and after I sample it. Then the delay of this scheme will be n times 1 plus a fraction. Then that one is more expensive, but it's faster. Not fundamentally faster. Asymptotically speaking, is the same story. But in practice, it will be a big difference. And there is something else. I'm not clocking it. Then the frequency of that has to be very high, around n times higher. This one has a clock, which is going from time to time, and I like that. Why do I like that? Then why do I prefer to have a slow clock? Less energy consumption. Less problems with glitches, with skews on signals and things like that. Then we like to have more parallelism if possible. It's not the case because in here is not real parallelism, but the clock is going slower. Then essentially, I didn't change the asymptotic complexity of the addition, but I have a more robust adder. And there is something else. Okay, this is a layout of how you make it. We don't care for that. Not that we don't care. We don't care now, in this moment. Okay, we care in general, because at the end of the day, what you want to have, it's a real chip. Now, there is something else. When I look at this guy, I see what is the worst propagation path. The worst propagation path will be whenever I have changes happening here and producing carries which are going down to the most significant position. This is the longest propagation path, and this will determine the cycle time. But I also see that not always this is true. Then I may have a carrier getting from here, and it may be absorbed here and will not travel here. And then the calculation will finish here before, and then I may have another carry from here, which will get to this point. Then this is the worst case for the ripple carry adder. But in practice, your ripple carry adder will have a reaction time which will not be constant. In some cases, you know, carries will appear and they will travel in the system and they will get absorbed. Let's say if I have here 0, 0, doesn't matter what I'm jumping here up or down, I'll have a carry here which is 0. There will be no propagation. Now, this is good if I do a synchronous design, because if I do a synchronous design, when I have the result ready, I'm raising a flag and I'm saying your result is ready, just take it. When I'm doing synchronous design, this is not useful, because in order to clock the result of my adder, I always have to wait for the worst case situation. And this is the worst case situation based on an assumption. Share with us.
We have just had a little discussion about which of the two options that you mentioned were synchronous and asynchronous, because we understood synchronous design.
No, I said asynchronous and synchronous.
Yeah,
Then asynchronous is when I'm done, I'm saying I'm done. Synchronous is I'm always waiting for the completion of the worst case, and then I sample the result. Sometime I may wait too long, But this is simplifying the story. Now, almost all your processors that you have around you are synchronous with a clock, because this is solving some other issues about complexity, about keeping things under control. But asynchronous solutions are better from the energy point of view. There is no clock. In a system, you waste a lot of energy for the clock. You know, but it's like the conductor of the orchestra. No conductor, no concert, even though you may have a good orchestra. Except if the orchestra is really brilliant, but that's most of the time not true. Now, you see, if you look at this diagram, you see that I said the longest path starts from the least significant position and ends up in here. This is based on an assumption that for such a full adder, the calculation, the delay from carry in to carry out, it's shorter than from carry in to the sum. If that's not true, then maybe different. This will depend on how I implement my full adder. But most of the time, this holds true. Why am I saying that from carry into the sum? Because these are stable since long time ago. Then when this carry is coming, those were stable. Those are stable at moment 0. The carry may come after some kind of propagation steps. Okay, this is a kind of like, you know, so assuming that in a system I have some adders and I don't know what to do with them, and I want to compute some functions, then I have some silicon which is already configured as adders. I can use that silicon in order to implement functions. And this is the implementation of a function based on this kind of configuration. You know, I'm computing f, which is w plus the product of x, y, z. By, you know, placing at the inputs of this 4-bit adder some signals, I am computing this function. You know, like I can explain this part and you can do the rest. Because carry 0 is 0, carry 1 will be 1 only when both of those will be 1. Then in here I'm computing this product. Because I put this 0, the output will be 1, carry 2 will be 1, only when this is 1 and this is 1. Then this is the next product. And now I have an OR and whatever. Okay, this is for Hami's kind of, you know, toy. It is an interesting, let's say, intellectual kind of, it's like a puzzle, if you want. Do we use that in practice? Most likely not. Or not today, because today we have FPGAs. And we configure that. But this might be an interesting trick. Okay, now I have an adder, and a part of the result, there are other things that I would like to know about the adder. First of all, I would like to know whether the result is correct or not. Remember, we do 2's complement. And when I do 2's complement, I have to be sure that my result is correct. Whenever I add a negative and a positive number, or the other way around, I always have a good result. But when I add 2 positive numbers or 2 negative numbers, it might be that the result is larger than the largest representable positive number or smaller than the smaller representable negative number. And I have to know that. Then this is called an overflow. And this can happen when both numbers are negative, right? This is the sign digit in 2's complement. This is one operand, this is the other one. Then if both of them are 1, are negative, and the sum is positive. That cannot be correct. Or I can have the same, an overflow when both of them are positive and the sum is negative. This is the definition of the overflow. When they are of different signs, I never fail. Now, there is a beautiful way of computing that, and this relies on an XOR gate, which is saying I would have an overflow whenever the carry out of the most significant position and the carry into the most significant position are different. This is another way to compute the overflow. This is the explanation of when the overflow can happen. It's a logical explanation. I can stand it with arguments. This is based on some algebraic derivations. You can try to prove that. It will be a very good exercise to demonstrate yourself that you can still handle Boolean algebra, which might be useful in the exam, you know. I keep on saying exam because I know you care for that. Not that I care for the exam. I always pass on computer arithmetic exam because I'm not taking it. And even if I take it, if I make it, I should be able to pass. I'm actually making the exam and I'm checking plus or minus the time which takes me to solve it. And I assume a ratio of, let's say, 1 to 3. Then if I solve it in 1 hour, you can solve it in 3 hours, right? Is that good? It's a reasonable assumption. Should I go for higher? Like 1 to 5?
Yeah, would be helpful.
Why?
More time for us.
No, come on. You have to demonstrate yourself that you are good. That's a challenge.
Okay, 2 hours.
Life
Should
is
that
full
be
of challenges.
3 hours? That particular 3 hours? Can that be another time? I mean, it can be fine.
Nah, you want time on another planet, right? What if we go closer to the sun? It's shorter, huh? Okay, now, that might be an interesting exercise to prove. This is essential. What else do I know? Do I need to know? I need to know if the result is negative or not. That's simple, because in 2's complement, I look at this bit, and whenever this is 1, it's negative. It's fine. I may also want to know if it is a 0. That's, conceptually speaking, very simple. Implementation-wise, not that simple, because I have to compute an OR over all the bits in here. Then if all those bits are 0, my number is 0. I can draw this gate, it won't do me any pain, but in practice, if I have 64-bit for addition, that will be a 64 NOR gate, which, remember the Fenin story? I won't do it like that. The way I will do it like a tree of gates. Then I will take a number of NANDs. I will do an optimization based on the technology which is available, and I will find the best tree which will provide me the 0 signal in the time which makes sense. Okay? Yeah, with us. They are not going away. They are very quiet. Some of them are looking on the window. I think it's very beautiful in Eindhoven on the window. But at least 50% of the students in Eindhoven are looking at the slides, which is a good yield. Okay, now those conditions and exceptions are important for the processor, because this header is always part of a processor. They are important for the processor to understand what we just did. We did an addition, but we have to know, for the branches mostly, what the properties of the result are. Now, in digital signal processing, like mostly in audio or video processing, you have some calculations where result, even though representing on, let's say, 8-bit, cannot take values larger than 200. They don't make sense because the intensity of the color can be between 0 and 200. And what you do in that calculation, you say, you make a calculation on the intensity, you get, let's say, 240, and because 240 is not a valid number, you will replace that result with 200. I'm giving you an example. This is multimedia processing. It's happening very often. What I just said results in a number of instructions. I'm doing the addition, I'm looking at the result, I'm comparing with the maximum. If larger than the maximum, I will replace my result with that constant. It took me already a couple of instructions. Now, to deal with that kind of situations, most of the digital signal processors do have a beautiful header which is looking like that. In here I have a ripple carry header or whatever header. I have the overflow, which is a signal which is telling me it's, you know, larger than something. I will compute this overflow depending on, you know, what my maximum value is. Then I will have to inspect the result in the same way I'm expecting it for 0. Then I will need some Tudelft gates. And then if the overflow is present, instead of selecting the result, I will select a value which is a saturation value, you know, which is hardwired. From the point of view of the header, I didn't do anything wrong. I put an extra multiplier on the output, a multiplexer on the output, sorry, which will increase a bit the propagation. But I saved a lot of cycles. I do that addition, I'm saying addition with saturation, and in one instruction, I solve that kind of, do the calculation, see if the result is larger, and things like that. Okay, that kind of operations are implemented in digital signal processors. Probably you heard about MAC, multiply and accumulate. When you do filters, okay, you may write in C, but the compiler will make use of that. Most of the DSPs, they have an operation which is doing a multiplication and an addition in the time it takes to do a multiplication. This one is doing an addition with saturation or with clipping. They are kind of similar things in one cycle, then instead of spending a lot of instructions. Those are simple tricks which we can do in hardware in order to speed up execution of programs. But our goal is to try to speed up addition. Because what we have, it's a beautiful simple header, which in general has a delay which depends on the operands. But if I use it in a synchronous system, I always have to wait for the worst case, which, you know, it's wasting time. Now, this is a slide which is presenting a carry propagation analysis. It's kind of similar with what I just told you some slides ago, that carries may appear, propagate, and eventually die. And in here you have, you know, carries which are appearing in this position, and in here I have a 1-1. Certainly I will get a carry, which will travel for a while, but will be absorbed here, because in here I have a 0-0 and cannot go further. And you see each kind of carry which is appearing, you know, I have carries in this column, in this column, in this column, in this column. They will propagate in an independent way in my header. And eventually, when all of them are ending the propagation, my result is correct and stable. And I can read it. And you see the chains are 2, 3, 6, whatever. Then in this case, the propagation will just take 6 stages in order to finish. If I assume different operands, it will take longer or shorter. Now, this can help me to try to design an header where I have a bit of smartness. Again, this will be good for asynchronous design. And this is called carry completion adder. And it's based on this kind of analysis, which is saying that I can assume that carries are generated with a certain probability. Then I have a probability to generate a carry, to annihilate a carry, and to propagate a carry. Now, in each position, I have 2 bits, which can be 0, 0. Now, the probability that both of them are 1 or are 0 is 25%. I'm assuming this uniformly distributed probabilities for the bits. The probability that they are 0, 1 or 1, 0 is 50%. Based on this analysis, I can compute some kind of things, and eventually this will tell me that the expected propagation path for a carry is about 3.5 positions. Then even though my operand is 1 billion operands, 1 billion bits, in most of the cases, the average propagation of carry is around 4 positions. Then if I can make my adder smart and equip the adder with a kind of signaling, I can get the result as soon as the result is finished. This will make sense in an asynchronous system. In a synchronous system, you always do things like that, right? This is your logic. You have inputs to the logic. There is a propagation, and then you sample the output in a register, and this sampling is working like a clock, right? Then whenever I have a rising, or let's say rising, I am sampling the output. Then for a synchronous system, the fact that I have the carry ready is not relevant because this clock is not listening to this. Now, if I have an asynchronous system, I can have the inputs here, I can generate the result, and instead of using the clock here, I have another signal which is ready. And then this will sample the output in a register whenever it's ready. Then if the calculation takes, I don't know, n ripples, it will be after n propagations. If the calculation will take 4-bit ripples, it will be ready after 4. I will always say, I'm ready now. Then in an asynchronous system, I have the best out of my operands and my hardware. Now, how do I do that? I do that by changing a bit my logic with what we call a carry completion detection. Now, remember the full adders? This is the full adder, this is the full adder. We had here a carry, which was 1 bit, 0 or 1. This carry were coming from here to here, and was only transporting a value. Now I put here 2 bits. And there are 2 pieces of information which are transported, the value and the readiness. If both of these bits are 0, this guy has to wait or cannot complete the calculation because this carry is not known. If I have 0, 1 or 1, 0, the carry is known, it's available, and it's 1 or 0, and can go further. Now, this will go on between all the full adders, which in the top of the full adder calculation will have that kind of extra circuitry. Now, if I collect all those bits which are telling me about the completion of the carry over all my adder, and I put them in an AND gate, then whenever those will be all set, I'm done. Then what did I achieve? I made the hardware a bit more complex because those boxes now are changed full adders. They do the same calculation, but the way I'm encoding the carry is different. Then those are a bit more complicated. The communication between those is now based on 2 wires, not on 1, but those are local wires. And what I achieved is an header which will tell me always when the result is available, and I don't have to wait. Now, this can save a lot of time and energy in asynchronous systems. And we would love to have only asynchronous systems. The problem is that we cannot have that due to other issues, like the fact that we are not able to deal with the complexity of such a design. When you make a simple asynchronous system, things are okay. But when you have many parts in an asynchronous system, you have a problem because there is no conductor to put them, in order. And you may lose control of the system, and it's very difficult to validate the system. You may have various combinations in your large system which may end up in what we call deadlock or live lock or some kind of other things which will give you a blue screen. Okay? Now, unfortunately, I have to stop for today. I know you would like me to continue, right? Or not? Then, I'll see you Wednesday. Did you try to solve the homework? Okay. You guys? No. And? Simple, you done it, right?